Okay, hello everyone. Hello. Okay. Hello everyone. Let's start our lecture. It's like day 12, Wednesday, February 17. And sorry for a little delay. I'm just opening my files. It was a little bit delay. Hopefully it will work right now. Yeah. So let me share my screen with you guys, and I'm ready to start. Yep. So basically, so we are in good shape with this course, and I do believe that by the end of today, you should practically be ready to do your homework 3, except for ideal gas topic, which will start on Friday. But there is something again conceptual that I ended up last lecture and that I want to start today. And this is what I did. It's topic, very key point topic, how we are able to identify the states. So basically, I recall one more time. I know it's boring, but at this point, I will show again everything one more time from now. But after this, you should be able to identify state. And if you don't pick up it now, you are already in trouble. And if you don't pick up it during a week, you're in big trouble, okay? So if you want to pass this course, you should be flexible with tables and know how to define the state. You remember all these diagrams. And the key point here is to assume it's saturated mixture, but not just assume, but check. And check if it's true or not. I recall how we are doing. I recall from last time. What's the question, please? For homework 3, is there only one appendix for it? What do you mean by appendix? I misunderstand a little bit. What appendix do you mean for homework 3? Could you please repeat your question? Anyway, let me proceed. So this is classical PT diagram, because I did not send any appendix for homework. So please clarify. Okay, so this is PT diagram. So what we are doing, again, if you did not listen me yet, listen now. You suppose this is a saturated mixture. Yeah, please also turn your microphones, because mute yourself because I hear somebody, right? Okay, property. Okay, the question was about tables. Yes, there is one file for property tables, but it's not for homework 3. It's for the entire course. You are mostly highly recommended to print it out by this time and start using and practice with them. And we will practice with them even today with you. And you will see that most likely you are slow and you should do it faster. It's your property tables. It's your key instrument, key tool for this course. Anyway, coming back here. PT diagram. Assume you deal with saturated mixture. If it's true, what does it mean? That you should be along this pink line. And then what you will check? You will check where you're here with respect to this line, above or bottom, left or right, and based on which you make a conclusion. Let's say you have temperatures. So let's find saturated pressure at my given temperature. Let's say I'm here. And then I will check Ym as compared to this pressure. What if my pressure is higher than saturated? It means that it's compressed. Pressure is high, it means that it's compressed liquid. It's more compressed than it should be to be saturated. Or if my pressure is less than saturated, so I have rarefied gas, it's superheated vapor. Eventually, if they really coincide, if my pressure is saturated pressure, then this is saturated mixture indeed. Does it make sense? And now from here, when you do this analysis, you know where to go. To compressed table, to saturated table, to superheated table, where to go. That's mostly important. Now, you go to examples. We discuss it and let's discuss again. Let's say I have H2O at 5 megapascal and 80 degrees Celsius. Like it's similar to example 3.8 in your textbook. So what you can do? I will check. So what is my saturated pressure at this given temperature? It's 47 kilopascals. So, but your real pressure is higher. It's 5 megapascals, right? So what does it mean? That you are here? You're at compressed liquid. So now you know where to go, and you go to table A7. Only now you should show this analysis. If you just guess and say it's compressed liquid, I may not believe you, because 1/3 of you will have, we have only 3 options. We have compressed, saturated, and superheated. So I may not believe you unless you show at least this analysis. Another example, let's say I have Freon at 400 kilopascals and 30 degrees Celsius. Again, so I will take my temperature of 30 degrees and see what is my pressure at this given temperature. My saturated pressure at this given temperature is 770 kilopascals. But this exceeds my pressure, which is 400. So where am I? I'm here, which means that I deal with superheated vapor. And then from here, you are ready to go to table A30, which is superheated. Again, you may do the same analysis for temperatures instead of pressure. So you take your fixed pressure and find saturated temperature for this given pressure and see where you are, less at the same point or higher. Here it is. So basically, let's say I take my pressure and find saturated temperature. So then I will see if my temperature exceeds saturated, it means that I'm here on the right. So it's superheated vapor. What is superheated? It's hotter than it should be to be saturated. Or if I'm here, it's subcooled. What does it mean? It's colder than it should be to be saturated. So, or maybe I'm here, then indeed this is saturated vapor indeed as it should be. And then we are okay. And now from here you can certify where to go to compressed table, superheated table, or saturated tables. And we solved the last time exactly the same examples. And now let's take I take saturated temperature, saturated pressure 5 megapascal. I take pressure of 5 megapascal, sorry, and I will find saturated temperature at this given pressure, which gives me 264 degrees Celsius. And now I will see that my temperature, 80 degrees, it's less than this one. So what does it mean? It means that I'm here, right? It's my liquid is subcooled. Why we call it subcooled? Maybe it's very hot tea, but it's subcooled because it's colder than it should be to be saturated at this given pressure. So it's subcooled liquid, and of course you go to subcooled table, which you already know. I recall subcooled and compressed is the same. Subcooled liquid and compressed liquid is the same point. It's the same concept. And this example again for Freon, for refrigerant 135. But now I fix pressure and find saturated temperature for this fixed pressure. And you know that my saturated temperature here, it's about 9 degrees, which is really less than 30 degrees I have in reality. So what does it mean? Where am I? I should have 10? No, I should have 9 degrees, but I have 30. It means that it's hot, I'm here. So it's superheated vapor. And you go to the table. So please realize, I don't say that you must to show this plot or previous one, but this is the analysis you should show to justify. And again, you may realize that here I repeat what I did before for pressure table. Of course, it's like I just repeat. But I do recommend that if you have pressure and temperature together, I do recommend you that you repeat it twice. Not maybe at the exam when you don't have time, but at homework. So you practice again and make sure you get correct answer. Because there are 2 classical mistakes that you can do. One mistake that you confuse what is saturated and what is your pressure. You will see when you have this relation, you will see, okay, which is saturated, what is your? Are you from left or from right from it? If you don't see picture, you may not see it. And second, of course, classical mistakes, you confuse liquid water table and the Freon table. So, and that is really not appropriate. In this chapter, you should be able to to understand how to deal with tables. Now, I recall this is for PT diagram. All saturated mixtures here are along one line. So for given pressure, temperature is fixed. So if you don't have P and T, if you have P and something else, this picture, this diagram does not help you. So let's recall what we do if you have, let's say, PV diagram, like you may see here. But it's the same will be for TV, and instead of volume, specific volume, here you may have enthalpy, entropy, whatever it is, internal energy. So what idea is exactly the same. Still, you suppose this is a saturated mixture, and then you check where you here. Suppose this is saturated mixture, and then see where, left, right, or here. And if it's saturated mixture, you should be indeed along this line, correct? From VF to VG, for instance, if you talk about volumes. And remember, all these points, they lie on one point in previous PT diagram. Everybody remembers. So what I do, again, I will take my specific volume and compare with VF. If it's less, then I'm left from this bell, from saturated liquid line, so I have compressed liquid. If I'm here, it means that I have saturated liquid. If I'm in between this way, if I'm here, if my specific volume is in between these two values, it's saturated mixture. Eventually, if my volume is equal to saturated vapor volume, it's saturated if some animal looks like a dog and barking like a dog, it's a dog. That's what we have. And if I'm here, if my specific volume is larger than saturated, then it's superheated, it's hotter. And from here again, you will go to the compressed table, superheated table, and saturated table. And the same for other diagrams. It can be TOP here, it can be UHS over here. And we solved examples, right? Let's say I have freon at given pressure and specific volume. This is my pressure, that's my specific volume. So again, what I do, suppose it's saturated mixture and check. So I will compare my specific volumes that I have here to what? To VF and VG calculated for this given pressure. So I will, how I can get them? From the saturated table, I will go to table A12, which is saturated pressure table. I recall we have two saturated tables, temperature-based and pressure-based. It's A4 and A5 for H2O, for water, and it's A12 for freon. So here you will have that VF is this one, VG is this one. So I will see that, where am I? I will see that my specific volume indeed in between them, which means that, okay, that's saturated mixture indeed. And now I can go to my saturated table and get what am I what. For instance, I may calculate quality. Does it make sense? So please, everybody understood what I'm talking now. That's the last point when I repeat it. Everybody should understand now how to identify property tables. But when you say identify states, there is like short answer and long answer. Short answer we just did here, you know where to go. But long answer will be just now, let's go to the table and calculate the value you need. Maybe you need to calculate some values. For instance, if you may look at example 3.8 in your textbook. And it's a good example that, for instance, the question, why I say about this example, because the question there was, please calculate, it was exactly parameters that we use here. It was exactly question, please calculate specific internal energy, U, specific internal energy at this pressure and temperature. So you already know that it's table A7. So who will give me the first answer in chat? What will be specific internal energy for this condition? Please. For bonus. What should I do? I go to which table I'm going? I go to table A7. Great, correct answer. Nathan, great. Okay, two people answered almost simultaneously. Excellent. But still a little bit slow. You should spend 20 seconds for this at your exam. You need to practice more. It's like a driving, I tell you. So yes, so what you're doing, you go to your table A7. Here is I'll show on my screen, but you better have it on in your hands. It's faster than on the screen. You go to pressure of 5 megapascals and your temperature is 80 degrees. So here you are, right? And here is your value that we're talking about, 333.82 kilojoule per kilogram. Yes, that's the answer. Now, but you may realize, okay, that this table is very rarefied. In this table, actually, you don't have many values in table A7. Moreover, that's all table. And basically, people already ask me, you see that there is no compressed liquid table for freon, right? So what should we do then? Okay, I will answer here. Remember, I actually told you that the biggest crime you may do in this course and in this chapter, at least 3, when you confuse table. You will get 0 points, unfortunately, because you must learn the tables. If you confuse the state, if you don't know if you're not able to identify the state, if you confuse tables, it's really bad. But, Now, I tell you there is one exception, and I already told you before, but let me recall it properly. There is one exception when you are eligible to confuse tables. Illegal. You know, guys, compressed liquid, it's all, what do you know about compressed liquid? We know about compressed liquid that it's almost incompressible. Somebody already compressed it. So its property does not change much. If you have cold tea and hot tea, you know their properties and they smell similarly and they taste similarly. So the properties don't change much. So they change, of course, but not much. So you are allowed to confuse, or say to approximate, not confuse, to approximate, property of compressed liquid by the same property of saturated liquid, and such a given temperature. Does it make sense for you? So this is your property, and that's what you are doing. Do you see my screen? So otherwise, do you see this point on my screen? So you are eligible to approximate it by this point. Not by this, not by given pressure, by temperature. They are very, because they are close. To justify it, okay, that's what I want to show you that we can do it. To justify it, again, let's go to example from your textbook. Do I have my your textbook here? Yes, I have it, I believe. And if you have your textbook with you, maybe it'll take a little bit time for me to open. I'm sorry, I did not yet. But it's example 3.8. And I want to show it on the screen rather than copy because it's very illustrative. Because what I will do now, we just solved this example. I will, yeah, here is the table. So basically what we will be doing here. Give me a second, please. What's happening? It's slow, it's a little bit slow here. So what I will do here, again, I will have another way to discuss the same story. So here I have water at 5 megapascal and 80 degrees Celsius. So what's correct point to do it? Like we did here, you go to table and say A7 and identify, and we did it, right? Some of you did it even on the screen, we did it, and we come to table A7 and we got it the 33.82 kilojoules per kilogram. Now, what I want to do next, I want to approximate it by the same quantity at saturated liquid. Here it is. Example 3.8, here it is. So basically, you see my screen, right? So basically, one point we already did. So correct answer is this one. So even if I increase a little bit my size here, yes, here it is. So basically, you know that if you have this pressure and temperature, you know that it's stable A7, but you should certify. You check if it's saturated or not, and then you will understand this and you get this value. But another way what you can do, you can go to saturated, you can go to saturated table. So what I will do here, remember, I can approximate it by saturated liquid. I can do the following. I will take VF at this given temperature of 80 degrees Celsius. So which table should I take then? Which table? It will be saturated table. Exactly, it will be saturated table. Not in five. Yeah, you can take very good mistakes that you mentioned. You may take table A5 because it is saturated, but it's saturated pressure table, and you talk about value at given temperature. So you better take table A4, which is temperature table. You go to table A4. When you tabulate temperature and everything else depends on it, and you take what? You need to take value at 80 degrees Celsius. So you have 80 degrees Celsius here, right? So that will be a saturated pressure as we calculated, and you will see all other values you need. For instance, this is a value for your specific internal energy. It will be 334.97. Do you see my screen? I hope so. So this is a value. This is a value you calculated. Okay? So, and you will see this value is really close. So if you go back to the problem, you will see that correct answer give you this, if you go to compressed table, but approximate answer give you not very different value. The error is only like 0.3%, 1 over 300. It's very small error, which means that indeed you can approximate this point by this. Very good point, like Tara wrote about pressure E equal to 5. Why not to use table A5? Well, because if you approximate it by given pressure, you will go to this point. And you see here there is a difference. For instance, we can actually check this. If you go to the table A5, why don't you do it? Instead, okay, if you go instead of table A5 and given pressure. So in table A5, you talk about pressure of 5 megapascals. Even maybe, yes, here it is, right? If you take 5 megapascals, here it is, what will be our value? Our UF will be for 5 megapascals. Well, it will be really different. It will be 3 times large. So definitely it's a wrong number, correct? Do you agree with me? So why we say this? Because because you say that, for saturated mixture P and T are coupled, but it's not saturated, it's still compressed. So please realize 2 points. First, one, it's only one exception that I allow you to do, right? You can approximate compressed liquid but saturated. Please never approximate superheated vapor by saturated vapor. Please never confuse anything else, only this one. And second, this I don't approximate, I approximate properties. So this is still compressed liquid, okay? It means that it still does not coexist with the vapor. If I put vapor inside, vapor will condense immediately. I just approximate a property. I just approximate compressed liquid, but I just approximate compressed liquid, but by superheated vapor, okay? Do you understand me? Do you understand me now? Okay. Example. Let's say you want to cook something delicious. You want to cook some Greek salad and people say, add a little bit meat of bear inside, okay? I just guessing. And you will say, okay, where can I get this delicious meat? So what you will do mostly? You will take meat of chicken or rabbit and put it instead, right? And you will eat it. So you just replace ingredients. But I don't say that chicken is a bear, right? I just say that their meat is similar, it are replaceable. It does not mean that they coexist. If I put chicken and bear in one cell, they most likely bear will kill this chicken. They will not sit together. They will not coexist. They are not saturated. I only say that their meat have some kind of similar protein, some kind of similar properties. That's my approximation. But if I approximate meat of bear by soda or by milk, it will be ridiculous idea, right? They're different. Do you understand why I'm talking this? It's only one exception. Please don't approximate it by UF at given pressure or UG or at superheated vapors. That's only one thing you are eligible to confuse. Okay? Does it make sense? Great. So I want to talk a little bit more about quality and about mixtures. We did not talk much. I introduced you to this point, but we did not talk much. So recall, when you have tables, again, table A4 and A5, they really look very similar. But in table A4, you have temperature, and then pressure and other parameters is a function of temperature. In contrast, in table A5, you have pressure and then temperature and other parameters as a constant as a function of pressure. So these are the same values, but they put in different ways. Okay. So now please remember, from these items, for compressed liquids, what do we have? We have two different substances, two different phases all the time. So for all of them, we have parameters. That's why we have VF and VG, UF and UG, HF and AG. They coexist. Do you understand? So subscript F corresponds to liquid, saturated liquid phase, because F is fluid, even I don't like it. Subscript G corresponds to saturated vapor phase. And value of G, it's not a physical quantity, it's just difference between them, because you will use it in some formulas. So this is the size of the plateau you have, right? So remember how it looked like in any kind of diagram. Yes, for instance, here. So this is saturated liquid, this is saturated vapors, and you in between them. So this plateau, if will be Vg minus Vf. So that's one thing when you're allowed to confuse. And for instance, if you have evaporation, definitely Vf minus Vg, Vg minus Vf, sorry, gives you your evaporation expansion. So just again, a couple of things to discuss. So basically, that's how your table look like, right? So here you have in your table values for saturated liquid, right? This is F values, I call it F values. And here you have G values. And FG values, it's the difference between them. So please understand what they are. And at this point, you must know it. And there is a concept of quality. So remember what is quality. It's fraction of the vapor in your system. Nothing else. It's fraction of vapor in your systems. But now, I don't want to waste more time on derivation, but you can look what you did. So if you have total volume, it's like liquid plus vapor volume. Then your average specific volume is what? It will be total volume by total mass. It's like this. So from here, you can easily come to the ideas that you can express total liquid and total vapor phase as follows. And then you have the specific volume is nothing but this. Specific volume is nothing but this. 1 minus x by this plus this. X is equality. You know what is Vf, what is Vg. Well, I will provide, you can, it's, and second formula is just different manipulation, and Vg minus Vf is Vfg, so by default, this is exactly as this. True? So you can easily check, what does it mean is if my quality is 0? If my quality is 0, then what? Then I have Vf, because these terms go out. These terms go out. These terms go out. In contrast, what happens if my quality is 1? If x is equal to 1, I will arrive to Vg. I will arrive to Vg in all the cases, right? Because if it's 1, they all go out. And this plus this will give me Vg. So it will be just Vg. Do you agree? Okay. Does it make sense for you? So if you know quality, you can find, and basically what I may say here, in fact, I think your screen sharing is paused. Why? New share. Yeah. Now it looks like I should. Strange. Something happens. Let me. Okay. I should share screen again. Sorry. It looks like I pushed some wrong button. Sorry, guys, girls. Well, now you see my screen, right? Again. Okay. So basically here, yeah. So basically I'm here, and if you know X, if you know quality, you can find your average specific volume. In fact, this is average, right? It's average value. It's total value divided by total value divided by total mass. Now, believe me or not, but I can write the same expression for all other quantities in your tables. Remember what do I mean by Y? What other qualities? It can be V, U, H, and S. You remember in your table you have specific internal energy, specific entropy, and specific volume. You have it there. So that it is. Okay? Do you agree with me? Do you understand me? So, and basically that's it is. So this expression works for any of them, and I can write like as follows. So my V is given by this, U like this, H like this. And moreover, do you see the similarity relations that I can write? That I can express my quality as follows. And of course, you may see that this term is nothing but this. This term is nothing but this. And this term is nothing but this. Correct? Excellent. And please look, this equation that I put it, even I put it in your equation list for your exam, it's really best to remember, it's really conceptual. Because it couples all variables we have. And do you realize now, like you realize two things now, that if I know any of these properties, I can get anything else. So if I know V, I can find X and I can find U and H and S and so on. If I know X, I can find anything. As soon as I know quality, I can find anything I need. Do you agree with me? And another point, please pay attention to it. I told you, well, it depends on convention, but I appreciate definitions that you can talk about quality for superheated vapor, and you can talk about quality for liquid phase as well. Because what it's vapor fraction. So what is quality of superheated vapor? I say it's always one, because it's a superheated vapor cannot coexist with something else. If it's not one, it means that it coexists, so it's not superheated vapor anymore. And what is the quality of liquid phase, of compressed liquid? What is it? It's zero. Why it's zero? Because, well, because if it's not zero, if there is vapor in the compressed liquid, it's not compressed liquid anymore. They cannot coexist. They are constant, they don't make sense, but they exist. While for saturated mixture, X, it's not a constant, it's some parameter that may change from 0 to 1. But, pay attention, this formula, it's for two-phase system. This formula does not work for superheated or vapor or compressed liquid. Why? I will tell you. Let's see. Let's say one of the student is not so clever, none of you, somebody who did not attend my lecture, okay? And this not very clever student uses formula just for compressed liquid. What is compressed liquid? For compressed liquid, your V is less than Vf. So for compressed liquid, you will get that your X is, if you use this formula, you'll get that X is less than 0. May it happen? No. Or vice versa. Another student will use it for superheated vapor. What do we know for superheated vapor? That this value V is larger than Vg. So for superheated vapor, you will get X is larger than 1. This formula gives you this, but it's physically fully ridiculous. So please understand why we penalize physical mistakes. It's not miscalculations. If you use this formula and you get that your quality is 1.5, it's not math error. Please understand what it is, because very often, again, not very clever students say that I say, what is X? They say, okay, it's something that you introduce on slide number 20. It's bad answer. You should understand. X, it's a fraction of vapor. If your fraction is 1.5, if your fraction is 150%, if your fraction exceeds the whole, you don't know what you're talking about. If your fraction is negative, you don't know what you're talking about. You are fully zero in this concept, right? It's not mathematical error. So please understand, your X should be from 0 to 1. Or let's say it's from 0 to 100%. Do you understand this, please? Is it trivial? Is it understandable? So that it is. So it's not enough to find the table. You should also go calculate. Yes, this formula, very good point. Yes, this formula technically works for saturated liquid and this formula, let me check again. This formula, okay, let me check what you wrote here. A very good comment, actually. Yes, this formula technically works only for saturated mixture. Yes, it does not, because it's derived for saturated mixture. It does not work. It does not work for superheated vapor or compressed liquid. It technically still works for what? It still technically works for saturated liquid and saturated vapor, because they are still like limiting case of mixture. Saturated liquid is still saturated mixture with no vapor, right? It gives you 0 and for liquid and 1 for vapor. Why we need this? We need this quality because, remember, if you have saturated mixture, pressure and temperature are not two independent parameters anymore. Remember this. This is your PT diagram, right? This is your PT diagram. You have line. If you have pressure, temperature is fixed. They are not two. These two values are not enough now to identify your state. You need something else, because remember, all qualities from 0 to 1, then they lie along this point. Please remember. So that's why we need quality like a parameter. And another point why it works here, you may realize that in fact on these diagrams with the bell, what is the quality? Remember geometrical consideration. In fact, quality is AB divided by AC. It's ratio. So definitely if you try to use it here, it will be negative. If your point, let's see, if your point B is left from A, your AB is negative. So your quality is negative. Similarly, if your point B is right from C, it's larger again, it's negative. Then it's larger than 1. Then AB will be larger than AC, which is physically ridiculous. Mathematically, you will get it. So that it is. You have saturated mixture. Your vapor cannot exceed the whole. Do you understand this, please? I hope so. So, and that's, yes, and that's these are examples we're talking about, and several examples are, you can consider, for instance, from examples, good examples are 3.4. Let's talk about examples, like there is good example 3.4 and 3.5 from your textbook, for instance. Let's say like this. So what we have in example 3.5? In example 3.5, it stated that you have freon. And this freon is, you may see here, it's already saturated mixture. So you have piece of liquid and piece of gas phase. Its pressure is this one. So you know it's saturated pressure. You know mass, total mass, and you know volume, which is 80 liters. The question is, please entirely identify the state. Let's say, so when I say identify entirely state, it's the following. It's not just enough to say it's saturated mixture. You should then go to respective table and get all data you need, all values you need. So let's do it. Let's see how you do it. So what you should do? Basically, it's example 3.5. Here it is. And you may see my screen here. So you have this value. So what should you do? You need to, you already know that it's saturated. You already know it's saturated mixture, right? How do you know this? Because vapor coexists with the liquid. So you already here somewhere. So you already know this. So you already know what will be your temperature. Your pressure is done. So you already know what will be your temperature. What will be your temperature? Your temperature will be saturated temperature at this given pressure. Here it is. You will get it from which table? From which table you can get it? It will be pressure table for saturated pressure table for freon, which is table A12. Yes, exactly. You need to practice and practice faster. That's good. Great. So what I do next? If I want to not just qualify it, but quantify, I should deal with numbers. So I need to find my quality. So what should I do? I can find my specific volume. How can I find it? Here it is. I know my total volume, total mass. So this is my average specific volume. Average specific volume. Do you agree? And now you should be able to understand that it should be between VF and VG. You may check, so where you get this VF and VG? Again, from the same table, it will be table A12. If you go to table A12, you will be able to calculate it. You will calculate this value for VF and VG. Let's say HF and AG, correct? How you will calculate? You will get it from the table. So for instance, you go to, where is your tables? You go to table A12. Here is table A12. You know that your pressure is 160 kilopascals. So you talk about this line. And in this line, you know what you need. Here is your saturated temperature. And here all the values you need, for instance, VF, VG, UF, UG, HF, AG. If VF values are also here. So here they are, and here you can find whatever you need. Here you may see the value. If you need enthalpy, here is value for enthalpy, here is value for AG, for volume, and so on. Does it make sense? So, where am I? Here am I? Yes. So basically that it is. If you know your values, you will be able to find your quality. How will you be able to find your quality? Here is the formula. I gave you this formula, right? Find the quality. And when you know the quality, you will be able to find everything else from here. Everything else. So here it is. So here is your quality. And from here you have this value. Do you understand this? Here it is. So your quality is like 15.7%. It's okay. The key point that this quality is not larger than 1 or less than 0. And to make sure, you should understand that the V that you calculated here, this value should be in between these two. If occasionally it's not in between, something is wrong. You should have this relation, right? So I find my quality. And when I found my quality, I can find anything else. So for instance, I want to find specific enthalpy. How can I get it? Here is my formula. I can get HF, I can get AG, HF. So I get this value, this, and calculate. And eventually, so here is my enthalpy is 64.1 kilojoule per kilogram. Does it make sense for you? Will you be able to do it? Great. Now, if I want to find total value, for instance, my total enthalpy will be what? It will be mass multiplied by specific enthalpy, which gives me what? Which if you multiply my mass by this value, it will be what? It will be 256.4 kilojoules. If I multiply this enthalpy here, and I have mass of 4 kilograms here, right? And you may understand the same will be for total volume, even I may know it here. And the same will be for total internal energy and so on. So that is what means whole analysis, that you're able to identify all values. Please, will you be able to do it? I hope so. Another example, here is it. For instance, the question is the system contains two-phase liquid vapor mixture at 6 degrees Celsius and the quality of 0.4. So you know it's saturated mixture already. Please determine the specific volume. So what should you do? Again, you go to temperature table because you have temperature. And this temperature table, go to this temperature line, and here are all your values. Here is VF and here is VG. And you will use this formula to calculate. And that will be the answer. The same will be for V, the same will be for U, for H, for other parameters. It's symmetric. You know quality, you know everything else. Does it make sense? Okay. Now, there is some important point that I want you to tell. So, like, yeah, assume you know what to do now. But there is classical mistakes the students do later. In reality, most likely, especially it will be in chapter 4 and later, we don't deal with one state. We deal with the process when you go from one state to another, right? So the key mistake the students do is like this. You identify state, and I assume you did it well. So you assume it's saturated mixture, you check it, you go to correct table, you found values. But then you extend your knowledge to state 2 based on this. So your state 2 may be different from state 1. It is different. It may be and it will be in different phase. So for each state, you have state 1, state 2, state 3, state 4, state 5. You should solve the same problem from the very beginning. They may assume it's saturated mixture and check. Does it make sense? You cannot extend your knowledge right away. Like I say that you ask me, what is your weight? And I write, my weight is mg. My mass is known, my g is 9.8 Newton per kilogram. I multiply and get my weight. But if I go to Mars, remember your homework too. On Mars, I cannot write mg. I can write mg, but g is different there. It's not 9.8, it's not universal constant. On Mars is different. I cannot extend it. The same story here. Please look at the screen and let's solve the problem, because that's a nice problem. It's stated here that I have piston cylinder assembly which contains it's like here, I have 2 kilograms of water. It's a water, but it's not just liquid water. It may be anything, we don't know. And this is state 1. So at state 1, I have this given temperature and pressure. Pressure is 1 bar. So can we identify state 1? Let's identify. That's your key point, to identify state 1 if it's not known, because otherwise you cannot use. And you will see how you identify. Like usually you say, assume the saturated mixture. What is your pressure at this temperature? Your pressure will be quite close to it, but it will be atmospheric a little bit higher. So from here, you will get that it's a little bit rarefied, so it's like slightly superheated vapor. It's here. It's close to saturated, but it's superheated. And you know the state. So you go to superheated vapor table and get these values. Do you understand this? Okay. You know how to do it? So you'll go to superheated vapor and find 1 bar, 100 kilopascal, and get properties for this value. So if I ask you while I'm talking about this, what will be value U here? What will be U1? Please go to a table and give me the answer. What will be U1? Please write down in the chart for bonus. I will, but you know how to find it, right? But now read the text. It stated that now your water is compressed to saturated vapor at 2.5 bar. So now you will have state 2. And your state 2 differs from state 1. Forget about state 1. It's different pressure. So what do you know about state 2? You know you need 2 parameters. You know only pressure. You don't know temperature yet. But it stated it's saturated vapor. So you already know everything. So what will be here? Then what are your parameters? So you will have that your U2 will be what it will be? It will be UG at this given pressure, P2. Your H2 will be what? It will be HG at given P2. And so on, so on, so on, right? So you know this one. And that's key point to understand. And for instance, later it stated that during this process, we have energy goes from water to its surrounding, and you lose heat in the amount of 250 kilojoules. You lose this heat, 250 kilojoules. What will be work done in this process? So what you are doing? Key point you already did. You calculated this value. So I ask you what is U1, and now let me ask you what is U2. Write down in the chart if you can. Who will be the first will get ticket. Bonus. Not penalty ticket, bonus ticket. Now, then in this problem you will employ first law of thermodynamics. How your first law looks like? Here is your first law. You don't have kinetic and potential energy, so this will be your first law. What is your Q? Your Q is given. It's minus 250 kilojoules. Okay, it's minus 250 kilojoules. Why minus? Because it's lost. That is what you need to find. What is this value? How to calculate this value? It's delta U. It's nothing but U2 minus U1. That is what? M U2 minus U1. Correct? So if you will you be able to calculate this value from the table, this value from the table, this value from the table, this value from the table? Well, this value will be need to find. So that it is. In other words, so that's what you do. Anybody answer to me? Then I will answer. Okay, you gave some data here. Okay, good. So here it is. I will write this formula from here. Q is what I will have. And now I need U1 and U2. And again, as you remember, state 1 is superheated vapor. So from here I know pressure, temperature, and my table gives me this value for U1. And what about U2? For U2, you will have this value. Okay? For U2. For U2. And then, what is W? It gets from here. You know Q, you know this value. So from here, you easily calculate what is work done. And you will get that your work actually is negative. Why it's negative? Because you have compression. Remember, your system was compressed from 1 bar to 2.5 bar. So your system has been compressed. It's compressed. So work is negative. It's done on the system as it should be. But key point, I want you to explain how to solve it, because that is conceptual here. The work is done on the system. These are the type of problems that we will be solving in actually more in problem 4, in the chapter 4. But even in your homework, I gave you some problems like this. And I will finish soon, but I want you to recall. So please open, if you look at your homework, I will not show you solution, I just show you assignment. Homework 3, right? Here is my homework 3 that we posted. So, remember last two problems. Not last two problems, sorry, problem 4, last two problems before ideal gas. Problem 4 and problem 5. Let's look. Problem 4, what is stated here? You have 3-piston cylinder assembly which initially contain 5 kilo of H2O at given pressure and temperature. So read the text body. You have initial state, this is state 1, so you have this pressure, this temperature, so this is P1, this is T1, right? And you have mass. So from here, will you be able to identify state 1? You will be able. But then it's stated that your tank is gradually cooled to what? To temperature this. So this will be new temperature. So you will have state 2. So please realize, you will have state 2 here. State 2 is different from state 1. It's a process. You will go from state 1 to state 2, like we just did here on our previous screen here, right? Like here. Yes, like here. So you have process from state 1 to state 2. Your states may be different. So you should solve the same problem from scratch for state 2. You have T2. What do you know about another state 2? It looks like you don't know anything, but read the problem. It's 3-piston assembly. 3 means that pressure will be the same. So it means that P2 will be still the same, P1, because it's given. Then you know both P2 and T2, and you should be able to identify state 2 and solve it. And then it will be questions plotted in PV diagram, what will be in energy in final state, at initial state, and so on. But your key point is the following. State 2 differs from state 1. Identify state 1 as I taught you today. And then forget about state 1 and identify state 2 from scratch. And also read the text. Words from the text give you equations. Like the process can be, if you stated 3-piston, pressure is constant. If it's stated adiabatic, Q is 0. If it's stated isothermal, temperature is constant. For instance, you have another problem. Problem 5, again, it's stated rigid tank initially contained some value of H2O at given pressure and given temperature. Again, this is P1, T1. You will be able to identify it. But then it's stated it's cooled, and this is T2. What do you know about state 2? You know temperature, anything else? The answer is that you have rigid tank. Rigid tank means volume is the same. So it will mean that your V1 is equal to V2. And if you divide it by mass, your specific volume at state 1 will be specific volume at state 2. So now you have two parameters for state 2, you will be able to identify it. So please realize, you have state 1 and you have state 2. Okay, guys? That's how you should do this homework. Okay, I will stop at this point. And what you will see from here, that except for multiple choice question and problem 6, now you are ready to do your homework. Please do it. And on Friday, we'll start talking about ideal gases. That's important topic. We will do it on Friday. Please do your homework. Start doing right now. I recall your help session will be Monday and Tuesday. And on Wednesday, homework is due date. And on Friday, next week, February 26th, you will have your exam, which is serious and it's more important. Okay, I'm stopping at this point, and